Okay. So, we have started the discussion of frequency compensation techniques and the problem of the stability of circuits when connected in feedback loop. So if you remember, basically, if we have a loop like this, the relationship between output and input is provided by this expression. Okay, where typically little a is a function of the angular frequency, while f is an attenuation function. So basically f is less or equal to 1. When the product a of a times f is much larger than the unity, we have that V out over V in can be approximated by this formula, 1 over f. Okay, so when we are analyzing the stability of this expression here, we should solve this equation and find the roots, the poles of the denominator. The poles must be with real part negative in order to have stability. But what we have discussed in the previous class is that we can even look purely at the product f times a and apply the Nyquist criterion. This quantity is the so-called loop gain. It is also referred to as T. Okay, it is a function of frequency, of course, angular frequency. And if we look at this quantity when it is equal to 1, so if we find the so-called omega 0 dB angular frequency, then we have that the phase of the loop gain can be fruitfully employed to investigate the stability, in the sense that if the phase curve is larger, so if the phase value is larger than minus 180 degrees, we do have stability. Okay.
I'm sorry, is it possible to move the screen towards right?
Okay, so yeah, I will try. I'm afraid that it is not possible, but I will try to do it this way. Nothing changed. Maybe I can try to just move the script. Just 1 second. Okay, so let me write the equations here. So basically, the gain, the global gain of the circuit is little a over 1 plus a times f. This is equal to 1 over f when a times f is much larger than the unity. Okay? We can focus on this quantity here, which is called loop gain, and usually referred to as T of omega, as a quantity to analyze the stability of these transfer function. Okay, so in particular, we will find the angular frequency which corresponds to a modulus equal to 1 if T of omega is equal to 1, this means that in dB, this is equal to 0 dB, as you may remember. So this quantity here, the angular frequency corresponding to this condition will be referred to as omega null, or omega 0 dB. Well, when we consider the loop gain in correspondence to omega null, and we look at the phase, we have to check whether the phase of this transfer function is larger or smaller with respect to minus 180 degrees. If it's larger, then we are in stable condition. Otherwise, we are in a condition in which the poles have a positive part, and therefore we have instability. Okay? So since we have to verify that this phase is larger than this quantity and the phase is negative, basically what we have to do is to compute 180 degree plus the phase margin, plus the phase, sorry, for T when we are in omega null. Okay? How do we use the Bode plots to analyze these quantities? Okay, so first of all, we start from the sketch of A of j omega in terms of modulus. Okay, so we know that A of j omega will be flat until we hit the angular frequency which corresponds to the first pole position. After each pole, we will be losing minus 6 dBs per octave, or if you want, minus 20 dBs per decade. Okay? So after P1, we have a minus 6 dB amplitude loss per octave. Then after P2, we will have minus 12 dB per octave loss in the amplitude, and so on. And minus 18 after P3. Okay? So this is A of j omega. We can then represent the phase of A of j omega, taking into account that each poles generate a 90 degree phase loss. In particular, we will be losing minus 40 degree before the pole and another minus 40 degree after the pole. Okay, so for example, here after P1 we have this minus 45 degree loss. Then the phase tend to further decrease during the first pole. Then we have the 90 degree phase loss due to the second pole, and finally another 90 degree phase loss due to the third pole. Okay, so at a very high frequency we have a phase value of A of j omega, which is around minus 270 degrees. Okay. What is interesting to observe is the fact that 1 over f typically does not depend on angular frequency. So the phase shift, the phase curve of A of j omega is practically coincident to the phase curve of the loop gain. So once we are sketching A of j omega, we are the phase of A of j omega, we are also sketching the phase of the loop gain. Another important consideration is that the global gain of the circuit is 1 over f. So we can draw the line 1 over f in this plot to compare little a of j omega with respect to 1 over f. In this case, f is equal to 1 in the case represented in this plot. So this means that also 1 over f is equal to 1. So basically, the global gain of the circuit, capital A, is equal to 1. Okay. Again, if we compute 20 logarithm base 10 of 1, the result is 0. Okay, so 1 corresponds to the 0 dB line. Okay, so this 0 dB line, it's the A of j omega curve in this point here. Okay, so important issue, T of omega is equal to A times F. Or, if you want, A divided 1 over F. If we compute the logarithm of this quantity, we have that this is equal to the logarithm of A minus the logarithm of 1 over F. Okay, so the dB's representation of T of j omega is the logarithm, the dB representation of A minus the dB representation of 1 over F. So for this reason, the distance between this curve here, the A of j omega curve, and the dashed line here, this distance here corresponds to T. Okay, so basically T can be found by shifting the 0 dB axis to the value of 1 over F. Okay, so T can be found this way. So let's recall that the Nyquist criterion should be related to the condition in which T of omega is equal to 1, again equal to 0 dB, then it is evident that this point here is indeed omega null, okay, omega 0 dB. So do not hesitate to interrupt me if these concepts are not clear, because these are quite important concepts that we will be using a lot in the next few classes. Okay, so let me analyze another example. So, for example, in this case, once again, we have A of j omega, which is the solid black curve here. Then we have the 1 over f curve, which correspond to the gain, basically, of the circuit when A times f is much larger than the unity. And then we have t, which is given by this distance. Okay, so this quantity here is t of j omega. Okay, the loop gain. Okay, in this case, this is indicated by letter x, little x. Okay, so the problem is that if we look at again at this plot and we check the value of the phase in correspondence to omega null, we have that the phase is around minus 100 and minus 270 degrees, which means that it is less than minus 180. So the circuit, it is clearly unstable. Okay? How can we turn an unstable circuit into a stable one? Well, we have to apply frequency compensation technique. So, for example, one way to make the circuit stable is to add deliberately a new pole to the circuit. Okay, this is called frequency compensation with dominant pole. After the addition of this new pole, what we get is that we introduce the minus 6 dB per octave amplitude loss much earlier than before. Okay, so in particular, we have that, you see, after the addition of this new pole, the new A of j omega curve is the dashed one. F is not changed, has not changed, okay, so is equal to 1. So basically, we have a new omega null. Omega null is now coincident with this point here, okay, where the dashed curve, it's the red dashed curve. What about the phase curve? Well, the phase curve experiences a new phase shift, a new phase loss due to the addition of the dominant pole. So we have this minus 90 degree phase loss. Then we have a minus 45 degree phase loss, which is due to omega null. Because it is coincident to P1. Okay, so P1 generates this minus 45 degrees phase loss. So the bottom line is that at omega null, the critical frequency for the Nyquist criterion, we have a phase curve which is quite larger than the minus 180 degree curve, which is the condition to have stability. So after the addition of the dominant pole, indeed, we have a phase margin which is equal to 45 degrees, and therefore we have stability. Okay, so this is one possible way to compensate the frequency response in order to have the stability. So by the introduction of the dominant pole. One interesting aspect is that in many practical applications, you indeed want this phase margin to be equal to 45 degrees. So the technique to achieve this goal is to have indeed an omega null which is equal, to the P1 value. Okay, so what was the former dominant pole, P1, now is the second pole of the circuit, and it is coincident to omega null. Okay, when we have this condition, we have the minus 90 degree phase loss, then we have the minus 45 degree phase loss. Therefore, we have exactly the phase margin equal to 45 degrees. Okay, so one possible way is to set PD in order to have omega null equal to P1. Okay, so again, PD is deliberately introduced by us as designer. You can see this as P dominant or P designer. Okay, the designer introduces this pole in order to have stability. If we want stability up to a phase margin equal to 45 degrees, we set PD in order to have omega null equal to P1. How can we do that? Well, first of all, we must take into account the fact that we know the value of A null. And we know that after the addition of the pole, we have a minus 6 dB per octave decrease in the amplitude. What does it mean, minus 6 dB per octave in practice? It means that when we double the frequency, so after an octave, think about the musical scores, okay? So one octave corresponds to a note which is double of the frequency of the previous one. So when we double indeed the frequency, we have a reduction by a factor of 2 in the amplitude. Similarly, minus 20 dB per decade means that if we increase by 10 times the frequency, we decrease by 10 times the gain. So along this curve here, the product between the gain A of j omega and the frequency is constant. Okay? Because any increase of the frequency is compensated by a decrease of the amplitude. This means this is valid through all this line, okay, up to this point. Okay, so in this point here, we have that the product is A null time PD. In this point here, the product is equal to 1 time P1. But since we have this constant relationship along this curve, this means that this quantity, same issue as before. So A null time PD should be equal to 1 time P1. Okay? So to set PD, we must comply with this relationship. So this means that in practice, we must force PD to be equal to P1 divided by A null. Okay? So let me recall the fact that phase margin is computed as the distance of the phase curve with respect to minus 180 degree when T of j omega modulus is equal to 1. So PD controls indeed the position in which we hit the 0 dB line. Okay, so we can set PD in order to have this hitting precisely when we hit P1. Okay, so this is basically what is explained in these notes here. Okay, so the idea is that once again, PD must be equal to P1 divided by A null. Okay, then this is transformed into a frequency value rather than an angular frequency, and therefore it is divided by 2 pi. Okay. Well, on a quite important note, we have that we have computed this PD value assuming a perfect asymptotic plot, while actually we have a reduction of 3 dB in correspondence to this frequency value here, P1. So the actual value of omega null is slightly shifted toward lower frequencies with respect to our initial estimation. Okay, and this generates also a slightly different phase margin. Okay. Another technique to minimize, to achieve stability is also by using a lower feedback. Okay, in the sense that if we are lowering the feedback, that is, if we are picking up a value for f smaller than 1, then we are shifting this line upward. Okay, so this dashed line is moved upward because this dashed line corresponds to 1 over f. So if we are decreasing the denominator, we are increasing the global transfer function. If we are moving up this line, this means that the T null, the T equal to 0 dB point occurs at a slightly lower frequency with respect to the previous condition in which f was equal to 1. Okay, so the omega null value is then shifted here. Okay, this means that the phase margin becomes larger because the pole position are unaffected, so the phase curve is always the same, but omega null, it is at lower frequencies. So this means that we have a larger phase margin with respect to the previous condition. Okay, so if we can guarantee stability for f equal to 1, then we can be 100% sure that our circuit will be stable also if f will be smaller than 1. Okay, that's why in practical design often the stability analysis is performed in a unitary feedback condition, because these conditions are the most critical for stability issues. So if we repeat the analysis in the new case with f smaller than 1, and we wanted to set the phase margin to be again rigorously equal to 45 degrees, what we need is that the dashed curve passes around P1 when we hit the 1 over f curve. So in this case, we can repeat the same concept. So the idea is that A null time PD must be equal to 1 over f time P1. This means that the new value for PD will be equal to P1 over A null time f. It is important to remember that f is smaller than 1. Okay, so the new PD, okay, in this condition, let's call it PD prime, it is at higher frequencies with respect to the previous case. So if you remember, when f was equal to 1, the value of PD was P1 over A null. In this particular case, PD, let's say PD prime, is a bit larger because f is smaller than the unity. So the solid curve is the starting point when in the solid curve is again unstable, because if we look at this point, that is when A of j omega hit the 1 over f curve, we have that the phase value is again below minus 180 degree. So the phase margin is negative. So the solid curve is still unstable, but we need to add a dominant pole at higher frequencies to get the desired phase margin. Okay, Another possible alternative is, rather than adding a pole, a dominant pole, is to shift the value of P1. This is an interesting technique because typically allows us to achieve larger bandwidth. Okay, so the idea is that, again, the solid curve, the initial value of little a of j omega corresponds to an unstable situation. Let's suppose again that f is equal to 1. So 20 logarithm base 10 of 1 over f is equal to 0 dB. Okay. So this is for the solid curve the value of omega null. Omega null, once again, means a times f equal to 1. And then we have to check the phase curve in correspondence to this angular frequency, and we hit the phase curve in this point, which is well below the minus 180 degree curve. So the solid curve corresponds to an unstable situation. Now let's jump to the dashed version. The dashed version corresponds to the shifting of this P1 to much lower frequencies. So P1 is moved to P1 prime. When we have this situation, we have that after P1 prime, we start losing minus 6 dBs per octave. We go straight up to P2 because this P1 does not exist anymore. Okay, so P1 is shifted, so we have no more the pole here. So we get to P2. After P2, we have another minus 6 dB. So after this point, we will be losing a minus 12 dB per octave. Okay. What about the phase curve? After compensation, we have the minus 90 degree phase shift associated to the P1 prime value. And then we have the minus 45 degrees phase loss due to P2 up to P2, and another minus 45 degrees after the pole position. Okay, so in P2 we hit the 1 over f curve, so P2 is coincident with the omega null curve in this case, and therefore we indeed have stability. Okay, so again, stability means that A is basically equal to 1 over f. Okay, A is this curve here, either the solid one or the dashed one after compensation. 1 over f is the this horizontal axis here, because does not depend on frequency. So when this curve hits the 1 over f curve, then we have omega null. here we have to jump to the phase curve, and we have to check whether we are over or below the minus 180 degree curve. Okay. So what is interesting is that in the previous analysis, basically the bandwidth was coincident with P1. In the new analysis, the bandwidth is coincident with P2, which comes at higher frequencies, and therefore we have a larger bandwidth. Okay, this compensation achieved by reducing P1, it is applicable to the case of the two-stage operational amplifier. So the two-stage operational amplifier is this guy here. So we have the differential pair with the current mirror loading, and then we have a common source in the second stage. Okay. Indeed, we do have some parasitic effects associated to this node here. We will call this parasitic effects C1. And we do have a certain load to be driven, C2. And then we have this capacitance value here, which is called Miller compensation capacitance, or simply compensation capacitance, CC, which is added to the circuit deliberately, okay, to achieve indeed the pole splitting effect, the shifting of the dominant pole. How this is this achieved? Okay, so we have to get back to the analysis of the two-stage configuration, okay, that we did, that we have analyzed a few days ago. So basically, the topology that we have seen in the previous slide can be represented schematically in this plot in terms of small signal analysis. Indeed, we have a first stage which has a certain current which is proportional to the differential voltage, and we do have an output resistance of the first stage. Then we have some parasitic effects associated to the intermediate node between the two stages. Then we have the compensation capacitance, C or CC. Then we have the common source stage. The common source stage is mostly given by the transconductive effect associated to this guy, transistor M6. Then we have C2, and then we have R2, which is basically the output resistance, okay? It is given by the parallel of the output resistance of the common source and the output resistance of this current generator, M7. Okay, we have already analyzed this configuration, this topology, because this is basically coincident with the analysis we have run for the common source topology, okay? So with a non-ideal input. So if we compute the relationship between Vout and IS by applying simply the Kirchhoff law, we get this expression. Okay, this expression is characterized by a first order function as the numerator, therefore we have 1, 0. And then we do have a second order function as the denominator, therefore we have 2 poles, okay, 2 roots in this denominator. Okay, after the break, we will analyze the pulse value. The zero can be easily found by nulling this quantity here, which is done when the angular frequency of the zero is equivalent to Gm over the compensation capacitance. Okay, so let's have a short break and then we will discuss the pole splitting effect. Okay, so indeed, the transfer function for this configuration is characterized by this relationship. We have said that we do have a 0 whose value is Gm over compensation capacitance. And please notice that this 0 is positive, okay? Then we do have the denominator whose roots are the poles of the circuit. So we went through the calculation of these poles and we found that the dominant pole is approximately given by this expression here. So if you remember, this is also called the Miller pole. Okay, so this pole is generated by the multiplication of the capacitance by the Miller effect. So the multiplication of the gain of the second stage. So the time constant is resistance of the first stage, output resistance of the first stage, gain of the second stage, time compensation capacitance. Okay, this is basically CC. Concerning the second pole is given by this expression. And what is interesting is that P1 tend to decrease as C increases, while P2, vice versa, increases as C increases. Okay, and in particular, when C goes to infinity, P2 is equal to minus Gm over C2 plus C1, because basically this term here becomes more relevant than this one, and then we can simplify this C with this C. Okay, so this phenomenon here is called pole splitting. Okay, so the poles which are initially quite close to each other when C is small or null tend to split apart when C is increased. Okay, so okay, just one quick comment concerning the second pole. Well, what we have is that the second pole is basically given by this expression when the compensation capacitance is sufficiently large, while for compensation capacitance equal to 0 is like having two independent circuits with two different time constant. First time constant is given by the product of R1 and C1. The second time constant is given by the product of C2 and R2. So basically, the initial value of P1 and P2 is quite comparable. Okay, so when we start adding a compensation capacitance between the first and the second stage, then the two poles tend to split. Okay, so this is the situation. This is the case for C equal to 0, with the two quantities quite similar to each other, closely spaced. And this is the condition in which the compensation capacitance is non-negligible. Okay, so if we increase the compensation capacitance, then the splitting of the pole increases as well. So this is the representation of this effect in the complex plane. What is interesting is to analyze this pole splitting effect in the Bode plot representation. Okay, because the Bode plot representation is the one that we typically use for stability analysis. So the idea is that initially we do have pole 1 and pole 2 closely spaced. Therefore, we have a quick, let's say, decrement of decrease of the magnitude after P2. Okay, so in the second case, we have the pole splitting, so this green curve corresponds to P1 placed at lower frequencies, while P2 is placed at higher frequencies. This is it. So the new P, let's say P1 prime is this one, P2 prime is this one. Okay, so we have the minus 6 dB per octave decrease in the magnitude after P1 prime, and the minus minus 12 dB per octave after P2 prime. In the initial case, we have here the minus 6 dB per octave decrease, and here we have the minus 12 dB per octave decrease. Suppose that this circuit is placed in a feedback loop, and suppose that the 1 over f curve is this one. Okay, so it is coincident with 0 dB value. So what is omega null in the two cases? Omega null, okay, or omega 0 dB. Can you point it? Okay, so where is omega null in this plot? Say stop. And we hit omega null. Omega null is the angular frequency which corresponds to a, little a, equal to the 1 over f curve. So we have the red line, which is the 1 over f curve in this point, okay? And then we have the green line, the second condition, which is the 1 over f curve in the same position, okay? So the idea is why it could be beneficial to have the green curve rather than the red one. Why the green curve is more stable than the red one. Well, you should try to imagine what happens to the phase curve in the two cases. Okay? Let's try to use our whiteboard to analyze this idea. For some reason I cannot. Okay. So now let's draw the phase curve. Let's start from the red configuration. This is the minus 90 degree, and this is the minus 180 degree line. Okay, so in the red case, we do have the first pole here and the second pole here. So in correspondence to the first pole, we will be losing minus 45 degrees, and then we lose other 45 degrees after P1. Then we hit P2. So we lose 45 degrees before P2 and other 45 degrees after P2. This is omega null, so we have to check the distance of the phase curve in correspondence of omega null with respect to the minus 180 degree curve. So in this second case, in this red case, we have a phase curve which is very close to the minus 180 degree one. So the phase margin is minimal, if not null. Okay. What happens instead in the green case? Well, in the green case, the first pole is located here. And the second pole is located here. So what about the phase curve? Well, the phase curve for in the first part of the frequency range is shifted because P1 prime occurs before P1. So basically we experience the phase shift due to P1 prime before the one of P1. However, P2 prime is placed at much higher frequencies with respect to P2. Therefore, the phase shift induced by P2 occurs at higher frequencies. This is interesting because if we compare the green phase curve to the minus 180 degree line, then we have a much higher phase margin. Okay, because the distance of this curve with respect to the minus 180 degree curve is much larger. So after this pole splitting, we may have a more stable circuit. Let's jump back to the presentation. Okay, so and basically the more we increase the compensation capacitance, the more we have the splitting, and therefore we typically tend to have a more stable circuit. There is one drawback, though, which is related to the zero effect. What is the effect of a positive zero? Well, on the left, you see the effect of the negative zero. So suppose that you have a first-order transfer function with a first-order numerator and first-order denominator. Therefore, we have one pole and one zero. Okay, so if F1 is smaller than F2, what we have is that after Phi1 we start to decrease by minus 6 dB per decade, and then after F2 we experience the zero effect, and therefore we have a plus 6 dB per octave. So the decrement induced by the pole is compensated by the zero. So we have a flat curve here. When we have a negative zero, in terms of phase, also we have a sort of compensation, in the sense that the pole generates a phase loss, while the negative zero generates a phase gain. Okay, so at the end of the day, at very high frequency, we have a flat gain curve and a flat phase curve placed at 0 degree. The effect of the positive zero can be quite, let's say, complicated, in the sense that, well, in terms of amplitude, the effect is just the same. Okay, the amplitude of a transfer function characterized by the presence of the zero means that after the zero we have a plus 6 dB per octave effect, which can compensate the effect of the pole, as we have seen before. The problem is with the phase. So a positive zero generates a phase loss, a 90-degree phase loss, same as the negative poles. Okay? And we have seen that losing phase can be complex, because what we are interested in is having a large phase margin, which means a phase curve much larger than minus 180 degree. So the phase loss induced by the zero could become a quite relevant problem. For example, in the two-stage CMOS op-amp compensation, we have indeed the effect of the first pole, so the minus 90 degree loss. Then we have the phase loss due to the zero and the second pole. And what is depicted here is the worst possible situation for stability, in the sense that this is the case in which the zero value is smaller than the second pole. So having a smaller zero is a problem, because basically the zero compensates the effect of the first pole, therefore pushes at higher frequencies the omega null value. So here we have the omega null value if f is equal to 1. This means that at omega null we are experiencing the phase loss due to P1, the phase loss due to the positive zero, and finally the phase loss due to P2. So in this condition, the circuit can be critically unstable. So how can we fix this issue? Well, basically we have to play with the zero positioning that is controlling the transconductance of the second stage and the compensation capacitance. So please remember that both these values are under your control as designer, because you set the transconductance of a transistor and you set the actual value of the compensation capacitance. Okay, so how can we play with these two quantities? Well, in this plot you see the effect of selecting different compensation capacitance values for a given technology in terms of the positioning of the dominant pole, the second pole, and then the zero. Okay, so you see that when we increase the compensation capacitance, we induce the pole splitting, so the dominant pole tend to shift at lower frequencies. The second pole tend to increase up to a certain point, up to the point in which the compensation capacitance is so large that the second pole depends just on C2 and C1, not anymore on the pure C value, the compensation capacitance. And the zero you see get to even smaller values than the second pole when the compensation capacitance gets very large. Okay, so is it clear, this plot? So these solid curves represent the trend associated to the second pole, so P2, the dominant pole, so P1. This is, let's say, frequency of the dominant pole time 2 pi is given by this quantity, and this is the frequency of the second pole time 2 pi. Okay, this is instead the frequency of the 0 times 2 pi. Okay, so when we have this separation, what is the effect on the magnitude of our frequency response? Well, for example, if we pick up the value 1 picofarad, for compensation capacitance, we have this red curve. So at this point, we hit the first pole, then we lose minus 6 dB per octave. Then at this point, we hit the second pole, where you see this point here, where we start losing minus 12 dB per octave. And at very high frequencies, we hit the 0 position. Okay, so this is the red curve case. The blue case is related to selection of a compensation capacitance equal to 0.1 picofarads. Okay, so in this case, the first pole is here, the second pole here is at this frequency, the 0, it is a very, very high frequencies. Okay. So after the first pole, we have the minus 6 dB per octave. After the second pole, we have the minus 12 dB per octave decrement. Okay. Finally, we have one last situation which corresponds to the black case. Black case is related to 10 femtofarad. So we hit the dominant pole here, the secondary pole here, and therefore the graph is this one. Okay, effect of the first pole, effect of the second pole. Okay, this black condition is most likely a condition of instability. Okay, because we have two closely spaced poles, so minus 180 degree phase lost achieved in a very short frequency range. The blue case can be more stable thanks to the separation. The red case, it is, let's say, the more stable combination, because the phase shift induced by the second pole, it is occurring at very high frequencies. Okay, when we further increase the compensation capacitance, the risk is in having the 0 placed at the same position of the second pole, which can be, again, dangerous. So this is how we play with the compensation capacitance to achieve the pole splitting. Since we have this relationship, you see that there is a clear relationship of the pole positioning also with respect to the transconductance value. So this is what it is represented in this second plot. So here you see what is the effect of increasing the transconductance in the pole position. Okay. So if you choose a transconducting value which is 1 microsiemens, then you have the first pole here, second pole here, and then the 0. Okay. If you choose a transconductance which is 10 microsiemens, then you have a better pole splitting, and the 0 is shifted at even higher quantities. And if you pick up a transconductance value which is 250 microsiemens, so you have a very large pole splitting, and the 0, which is also occurring at very high frequencies. So playing with the transconductance is also interesting because it allows you to have the same effect on the second pole and on the 0. So when you enlarge the second pole, you are enlarging also the 0, which is good news. Okay? So as an exercise, try to sketch this plot autonomously. Okay? Try to understand how this red, blue, yellow, and black curves are indeed generated. Okay? Try to reapply the same concept that we have used before. Okay, so after each pole minus 6 dB per decade, if we hit the 0 before the second pole, we have this effect, this sort of reduction of the slope, temporarily reduction of the slope. Okay. Okay, now I would like to use all the concepts that we have seen so far, including stability, to implement a strategy for the design of a two-stage op-amp. Okay, we have to combine the information related to the input-output swing, the slew rate, the DC gain, the phase margin achieved by the circuit to set the values of the dimensions, set the dimension of all the transistors in the circuit, and also set the value of the compensation capacitors. Okay, this is the design task. Okay, starting from the specification, find the value of the transistor which corresponds, which meets these specifications. Okay, to do so, let's jump back to the whiteboard. Okay. Okay, so first of all, let's discuss the input and output swing of this configuration. Okay, concerning the common mode input, we may have a maximum and the minimum value to have the saturation of all the devices in this circuit. Okay. Concerning the maximum value, we have to take into account that this guy should be on, which means here having a VGS due to this connection. This guy should be in saturation and also on. Okay. So basically, starting from VDD, we need a VGS here, so minus overdrive of transistor 3 minus threshold of the PMOS transistor. Then we need an overdrive here, so minus the overdrive of transistor number 1. But we need also an overdrive plus a threshold here. So the bottom line is that we need an overdrive here plus the threshold of transistor NMOS. So the maximum value, if we simplify this quantity with this one, will be VDD minus overdrive minus threshold PMOS plus threshold NMOS. Minimum value is the one which allows us to have this guy in saturation and this guy on. So starting from VSS, we had the overdrive of this transistor, which is transistor number 5. So overdrive of transistor number 5 plus overdrive of transistor number 1 plus threshold. Please remember that in this calculation, each VGS should be equal to this quantity, while the VDS should be equal or larger to the overdrive. Okay? Okay, so what about the output? The maximum value of the output will be equal to VDD minus the overdrive of this transistor. This is transistor 6, so this is the overdrive of transistor 6. The minimum value is VSS plus the overdrive of this transistor. This transistor is transistor 7, so overdrive of transistor 7. So basically, this is transistor 5, this is transistor 1, this is transistor 2, this is transistor 3, and this is transistor 4. In some cases, rather than expressing the maximum and minimum value for the output or for the input, it is defined the so-called headroom. Okay, so the separation between these values and the maximum possible values that we have, VDD or VSS. So, for example, the headroom for the output value with respect to VDD is equal to the overdrive of transistor 6. Okay, or the headroom with respect to the common mode input maximum value is the overdrive of transistor 3 plus VTP minus V threshold. Okay, so okay. Nevertheless, let's focus on these quantities here, and now let's consider another important effect, which is the so-called perfect balancing. So another important condition to be fulfilled. Okay, so the idea is that when we have this two-stage amplifier, we want the current which is generated here to be perfectly balanced in the two branches when we are in balanced condition. That is, when the negative input is equal to the positive one. How can we achieve this goal with a very good accuracy? Well, the possible discrepancy between the current which is flowing in this branch and the current which is flowing in the second branch is given by the fact that the VDS of this guy can be different from the VDS of this one. So these two guys under common mode conditions have the same VGS, but they may have a different VDS. Okay, so in this case, the VDS, even if has a minor role in the current setting when the transistors are in saturation, nevertheless, this role cannot be totally neglected because of the channel length modulation effects. So the idea is that to achieve a perfect balancing, we must impose this VSD to be equal to this one. So if this is the VSD of transistor 3, this is the VSD of transistor 4, this is transistor 6, 7, and so on, 5, 1, and 2. So we want VSD of transistor 3 to be equal to the VSD of transistor 4. To take this into account, we can consider the fact that the VSD of transistor 3 is also equal to the VSG of the same transistor. Okay, because this transistor has a diode connection. And the VSD of transistor 4, which should be equal to this quantity, is also equal to the VSG of transistor 6. And VSG3 is also equal to VSG4, by the way. Okay. Clearly, VSG3 is equal to VSG4 because source and gates are short-circuited. Okay, so let's take into account that the generic overdrive for a transistor which is in saturation is given by the square root of the current of the same transistor divided by beta. And that the VSG for a generic transistor is equal to the overdrive plus the threshold. We are discussing about PMOSes here, so let's write this way the result. So if we want VSG3 to be equal to VSG6 and 4, this means that since these are all PMOSes and the threshold is the same, this means that the overdrive of transistor 3 should be equal to the overdrive of transistor 6 and equal to the overdrive of transistor 4. And the overdrive is given by this expression when the transistors are in saturation. So this means that the square root of twice the current of transistor 4 should divided by beta prime p times the form factor of transistor 4 should be equal to the square root of twice the current flowing in transistor 6 divided by beta prime p times the form factor of transistor 6. Okay. We can simplify this expression. Rather than writing the W over L ratio, I will write simply the shape factor, okay, to simplify the notation. We can raise to the second power both the right and left-hand term, and we can cancel the terms which are in common. So the bottom line is that I4 over S4 should be equal to I6 over S6. Okay, this equation implies this one. Let me consider the fact that the VGS of transistor 5 is also equal to the VGS of transistor 7. Because, again, due to the short circuit which are in place. Therefore, with the same principles that we have used before, we can conclude that the overdrive of transistor 5 is equal to the overdrive of transistor 7. And as we have concluded from this relationship that I4 and I6 are linked by this relationship, we can conclude from this one that I5 over S5 is equal to I7 over S7, right? Okay, now one last step and then we will make another short break. What is the relationship between I6 and I7? Well, the current I6 is flowing through I7, through transistor 7. So I6 and I7 are equal. What about I4 and I5? Well, I4 should be I5 divided by 2 because we want the perfect balancing. Okay, so I5 is subdivided in two currents which are equal to each other. So I4 shall be I5 divided by 2. So, if we combine this equation with this one and these two, we can achieve an interesting result. So basically, we can say from this one that I4 should be equal to, I4 times S6 over S4 should be equal to I7. Okay? But I7 from this equation is I5 times S7 over S5. So this is I5 times S7 over S5. Okay, so this quantity here is equal to this one, but I4 is I5 divided by 2. So if we combine these two and we substitute to I4, I5 divided by 2, we have that S6 over 2S4 should be equal to S7 over S5. Okay, so the perfect balancing is achieved when we fulfill this relationship. So this is a strict constraint for the selection of the shape factor of our transistors. Okay, let's make another short break, and then we will review some other steps related to the design of the two-stage amplifier. By the way, the two-stage amplifier design is related to the project which I will assign to you after this, the completion of the first module of this course. Okay?
Ci sarà il farino.
C'è il from, se viene intendo, no, non rimane, se no no. Io lo so. Posso dire. Ti capisco, io sono grande.
Manca ancora uno?
Vai.
Allora, okay. So another important specification for these designs is the one related to the slew rate. Okay, so the capability of quickly increasing or decreasing the output value. So this is basically related to the maximum of the derivative of the output value with respect to time. To analyze this scheme, we have to take into account what we have discussed for the case of the single stage amplifier. So for the case of the single stage amplifier, basically you may remember that the load is placed at this node here, and when we apply a complete unbalancing, so when we apply a step function either to the negative input or to the positive one, then all the current generated by this transistor number 5, flows into the load capacitance. So in this case, the situation is somehow different because the load is not placed at this point, but is placed here. Okay, so we have to analyze what happens to the current which either charges or discharges this loading capacitor. So let's consider at first the case in which the positive input is applied to this topology. So I don't know why now I cannot cancel. So let's suppose that we indeed are applying a positive input here. Okay, so if we have this situation, then no current is flowing here, and all this current generated by transistor I5 flows into this branch. The current mirror duplicates the current input, so no current can flow even here. So I5 discharges this node. Okay, but if we are here we have high impedance, so I5 must flow through the capacitance, and it is then subtracted the charges through I5 to this node here. However, when we decrease the voltage at this point, we are enlarging the VSG of this transistor. Okay, so a quite relevant current will flow from VDD. Then we have also in the current balancing at this node the effect of this transistor number 7, which is driven by a constant VG gate voltage. Okay, so I7 is basically constant, while I6 and I5 are influenced by the biasing condition of this device. So we can say that the current which controls the charging of the loading capacitance is given by I6 entering this node minus I5, which is flowing in this direction, and I7, which is also flowing in this direction. Okay? So the slew rate, the output voltage derivative with respect to time is given by the current which is driven to the loading capacitance divided by the value of the capacitance itself. Okay, so V out is the voltage applied to this capacitor. So basically, we have this relationship. Okay, so the problem is determining which of these values are most determinant in the calculation of this derivative. So basically, we have to take into account the fact that when we pull down the voltage at this point, the VSG increases as well, and the VSG of transistor 6 has a quadratic relationship with the current which is flowing in the same transistor. So when we pull down the voltage here, the value of I6 increases very rapidly. So when VG2 is increased by virtue of the applied step function, we have that this current discharges the compensation capacitance here, and therefore we have a reduction of the drain voltage of transistor number 2, which means that VSG for transistor number 6 increases, and I6 as a consequence increases with a quadratic increment. So I6 typically is not a big problem here. Okay, so the problem in changing the value of the output indeed depends on how quickly we can discharge the voltage at this node here. Okay, because when we pull down this node, then the increase of the output voltage is very rapid due to this quadratic phenomenon. Okay, so the problem of studying the derivative of the output with respect to time can be transferred to the study of the derivative of the VD2 value with respect to time. And studying this transition means study the value of I5, because basically I5 is the quantity which charges or discharges the compensation capacitance, which in turn generates the voltage drop over V drain of transistor number 2. So basically, the slew rate that we have when we apply a positive step function is the minimum value between this term ICL over the loading capacitance and the relationship between I5 and the compensation capacitance, because the voltage drop over this compensation capacitance depends on the intensity of I5. Okay, so typically in this combination, I5 over the compensation capacitance is the smallest value, and therefore the slew rate for positive step function is equal to I5 over the compensation capacity. Well, when we apply a negative step function, the situation is somehow different, in the sense that we have, for some reason, sorry, I cannot. I'll try to restart or not. Okay, so now let's see what happens when we apply a negative step function, or if you want, when we apply a positive step function to this terminal here. So basically, in this case, all the current generated by transistor number 5 flows through this branch. No current flows in the other branch because of the unbalancing. And the current mirror indeed mirrors the input current at the output. And this current it is provided to the compensation capacitance for the charging. This guy is transistor number 7. This guy is controlled by a constant VGS, therefore we have I7 here. What happens here is that due to the flowing of I5 in this direction, we have that the voltage gain of the gate of transistor number 6 tend to increase. Therefore, the VSG decreases, and this means that I6 quickly vanishes because there is a quadratic dependency on the VSG. So practically no current flows into this transistor after in a very rapid transition time. So what we can say is that indeed this node sees I5 entering and I7 sorting out. Okay, so basically the current which controls the load capacitance, CL, is given by the difference between these two quantities. So I5 entering and I7 sorting out, okay, this node. Typically, I7 is larger than I5, and as a consequence of that, ICL is discharging the compensation capacitance. Okay, this means that discharging the loading capacitance. This is coherent with the fact that we have applied a positive step function at the negative input. So we are decreasing the output by virtue of this application. So the slew rate for negative transitions is basically equal to I7, minus I5 divided by the loading capacitance. This is what happens at the output, okay? Of course, we have also to fall into this region. We have also to charge this node here to stop I6. So basically, we have to take into account also the previous configuration. So the fact that I5 is needed to charge and discharge this compensation capacitance. So basically, the slew rate for the negative case is the minimum between these two quantities. If I7 is much larger than I5, then this quantity is larger than this one, and we can say that we can focus on the second term. Which is interesting because in this case, this means that the negative slew rate is equal to the positive one. Okay. Do you have questions related to this part? Is it okay? Great. So let's quickly review also DC gain, pulse positions, and zeros positions. So concerning the DC gain, basically we have the chain of two stages, the first stage and the second stage. The first stage is the differential pair. And the second stage is a common source amplifier. So the differential pair gain is, as you may remember, GM over the intrinsic output conductance of this transistor, which is transistor number 2, and the intrinsic output conductance of transistor number 4. And this is the transconductance of the element of the differential pair. Concerning the common source, this is transistor 6. So we have GM6 as a transconductive effect, and the output resistance is given by 1 over GO6 plus GO7. Okay, so the parallel between the output conductance of transistor number 6 and the output conductance of transistor number 7. Okay, so this is basically the DC gain of the two-stage amplifier. this is also what can be called a null. Okay, the gain, the DC gain. At high frequency, we indeed have the effects of the two poles and the zero. Okay, please remember that the dominant pole is induced by the Miller effect, which means that its value is given by the compensation capacitance CC time the gain of the second stage. So GM6. Let's call this quantity 1 over G06 plus G07, the output resistance of the second stage. So GM6 time output resistance of the second stage, while 1 over G02 plus G04 is the output resistance of the first stage. So the dominant pole is 1 over CC GM6 time R2, that is gain of the second stage, time resistance of the first stage. This is due to the fact that we are multiplying the compensation capacitance by the Miller effect, and the Miller effect brings this compensation capacitance in parallel to the output resistance of the first stage. This is P1. P2, as you may remember, is equal to minus GM6 over C1 plus C2, that is the parasitic effects associated to the first stage, plus parasitic effects and load capacitance associated to the second stage. Since the loading capacitance is typically much larger than all the other parasitics effect, we can say that P2 is more or less set by the value of GM6 divided by the loading capacitance. And finally, the zero. The zero, as you may remember, is positive, and it is equal to GM6 divided by the compensation capacitance. Please look at the frequency analysis of the common source stage to get an explanation of this zero development. Okay, great. So basically we have this situation here. Oops, sorry. We have a dominant pole, clearly dominant pole. Then we have a secondary pole and the zero here. So let's recall some basic facts related to the stability issues. Okay, so which are related to the positioning of poles and zeros. So first of all, the phase margin is equal to the phase of the transfer function computed when the the phase of the loop gain when the loop gain itself is equal to 1 in amplitude, plus 180 degrees. Okay. Let me recall also that when you have a complex number and you want to compute the phase, if the complex number is resulting from the multiplication of two complex numbers, then the phase can be found as the phase of the first complex number plus the phase of the second one. Okay, so if you have two transfer function, two amplification effects, the phase of the chain of the two amplification effects is equal to the summation of the two phases. Okay, this is a property of complex number. So, for example, if if A1 is a transfer function which is the one of a single zero, then the phase of A1 is computed as the phase of 1 minus j omega over z. And this is computed as the arc tangent of minus omega over z. The arc tangent is a function which is odd. This means that there is a sort of central symmetry. So this is the arc tangent of x, of a generic quantity x, and we have two asymptotes. First asymptote is at 90 degree, and this asymptote here is in minus 90 degree. Okay, so if when we have an odd function, this means that the arctangent of minus x is minus the arctangent of x. So the arctangent of minus omega over z is minus the arctangent of omega over z. If we are interested in computing the phase effects related to a pole, so if we want to compute the phase of a transfer function which is like this one, 1 minus j omega over, let's say, p1, we can say that this is equal to computing the phase of a function like this one, 1 plus omega 2 over p1 to 2 multiplied by 1 plus j omega over p1. Okay, so I've multiplied numerator and denominator times this quantity. Okay, so what we get is a number here which is real, so it has no effect for the phase calculation, and so we can focus on the numerator. So to compute this quantity, we have to apply the arctangent function to omega over p1. Please remember that poles should be negative. Therefore, we can consider the fact that the arctangent of omega over p1 can be written as minus the modulus of p1. Okay, so the bottom line is that we can rearrange this by writing this formula. So arctangent of omega over p1 is minus the arctangent of omega over the modulus of p1, because p1 is always less than 0. Okay, so in our circuit we have two negative zeros and two negative poles and one positive zero. Okay, so what we can say is that we will have our phase will be the combination of the effect of pole number 1. Then we have the effect due to pole number 2, and then the effect of the 0. Okay, and these effects are those indicated by this formula. So the bottom line is that to compute the phase margin, we will take into account the phase loss due to the first pole, the phase loss due to the second pole, and finally the phase loss due to the 0. So the phase margin will be 180 degree minus the arctangent of the angular frequency associated to the 0 dB value divided by P1 modulus minus the arctangent of omega null divided by P2 modulus minus the arctangent of omega null divided by the 0. Okay? Now, there are some considerations to be drawn here. First of all, we must focus on omega null. Okay, so the problem is, what is this quantity? How can it be found? Another consideration is related to then the positioning of P1, P2, and the 0. So to let's say to perform the global design, we have to apply some simplifying assumption. So we will suppose that P2 and the 0 are larger than omega null. Okay, so the idea is that our transfer function will be something like this. We will start from a value which is a null, and then at a certain point we will have the dominant pole, and then we will start losing 6 dB per decade. Then we will have the second pole position and the 0. Okay, we will need a similar situation, because otherwise, if P2 and Z are before omega null, then we will have a phase loss too consistent, and therefore no phase margin, basically. Okay, so P2 and Z must be after omega null. If we have a situation like this one, well, this is quite interesting, because we can apply the fact that again, we have an inverse proportionality between the gain and the frequency Okay, this trend, which looks like linear in a logarithmic plot, is actually an hyperbolic trend. So this means that the product of A null time P1 will be equal to the product of this point here. So 1, that is 0 dB, time omega null. So omega null will be related to the dominant pole position by taking into account the dck. Okay, very well. So let's suppose that we want a phase margin equal to 45 degrees. So we must plug this 45 degrees here. If we do so, we have that, well, actually what we can do is to move then this 45 degrees in the right-hand term and all this term on the left, or multiply everything by -1 to get this result. 135 degrees, that is 180 degrees minus 45 degrees, should be equal to the arctangent of omega null over P1 modulus plus the arctangent of omega null over P2 modulus plus the arctangent of omega null over Z. Okay, now some important assumptions. If omega null is placed at this position, we can say that it's quite far apart from P1. Okay, so basically, when we hit omega null, all the effects, all the phase shift induced by P1 will be completed. So basically, we can assume that this quantity here is more or less equal to 90 degrees. Please remember that the arctangent has this trend. Okay, so when x is sufficiently large, more or less the arctangent is equal to 90 degrees. Then we will make another assumption related to this part here. As a design choice, we will set the value of Z to be equal to 10 times omega null. The arctangent of 1 over 10 is equal to 5.7 degrees. Approximately. Okay, so if we have this condition that we will force as designer by tuning properly the circuit parameters, we will have that this equation can be simplified in this way. So we can replace 90 degrees rather than this arctangent. Then we will have the arctangent of omega null over P2 plus 5.7 degrees here. Made a mistake. Okay, so in conclusion, the arctangent of omega null over P2 must be equal to 135 degrees minus 90, that is 45 degrees, minus 5.7 degrees, so 39.3 degrees. So we can apply the tangent to both terms here, and find that omega null over P2 must be equal to the tangent of 39.3 degrees. This quantity is equal to 0.818, more or less. So this means that after some simple algebraic calculations, the modulus of P2 must be equal to 1.22, that is 1 over 0.818, time omega 0, omega null. Okay? So this is the positioning of the pole that we need if we want a phase margin equal to 45 degrees. Okay, tomorrow we will continue this analysis, also focusing on different phase margins. But please review at home this calculation. Okay, it's very important to understand all the mechanism. Arrivederci. Thank you very much for your attention.
Arrivederci.
Arrivederci.